Okay, so we're going to talk about a second way that we can combine functions now, and this is called the composition of functions. And this is probably new to you. You probably have not seen this before. So first, before we look at all those words, let's just look at this expression right here. Okay, so what is new to you here? Probably this notation. It's a little circle, and it looks kind of like a degree sign, but it's lower. Okay? So this is the way we represent the composition of functions. And the way we would say this is f composed with g of x. Okay, so f composed with g of x. And what this means is f of g of x. Okay, we have a function as the input, one function as the input to another function. Okay, so the domain of this function, so we say this is a composite function. Okay, so the words are we have a composition of functions, and this itself is a composite function. So the domain we'll talk about a little bit later in the next video. But something that's important, the product of functions that we talked about in the last video, f times g, is not the same as the function composition f of g, right? F times g, we just took f of x times g of x. That is not the same as f of g of x, okay? So some new terminology there, f of g of x, or f of g of x, and we say this is f composed with g of x. So let's do an example and see what this would look like. So it says, using the functions provided, find f of g of x and g of f of x. So we're going to change the order here. Okay, and one g of x is the input, and in the other f of x is the input. Determine whether the composition of the functions is commutative. So commutative means you can do it in any order. It's like addition is commutative with real numbers. So 2 plus 3 is the same as 3 plus 2. The order doesn't matter. Okay, do you think that's the case for composition of functions? Are these going to be equal to each other? Well, let's find out. Let's find f composed with g of x. Okay, and we could also write that as f of g of x. Okay, let's find out what this would be. So the first thing we'll do is the internal function here, g of x. Let's put that, we'll replace g of x with that value, which is 3 minus x. Okay, well, what is f of 3 minus x? Well, here's our function f. Anywhere there's an x here, we're going to replace it with the expression 3 minus x. So it's going to be 2 times 3 minus x plus 1, right? Okay, now we just have algebra. We just got to be careful. We distribute. We get 6 minus 2x plus 1. We get that that's equal to 7 minus 2x. Okay, so that's f composed with g of x. We've made a new function here. Let's do it the other way. Let's say g composed with f of x, which is g of f of x. Okay, we're going to replace this internal function with this expression. So this is going to be g of 2x plus 1. Okay, now everywhere there's an x in this expression, we're going to replace it with 2x plus 1. So it's going to be 3 minus 2x plus 1. Once again, we are careful of this minus sign to distribute it to all the terms. So it'll be 3 minus 2x minus 1, which is 2 minus 2x. Okay, are these equal to each other? They are not. Okay, so the composition of functions is not commutative. The order matters. F of g of x is not the same as g of f of x. Okay, so that's an important thing to remember. Okay, let's go back to the slides and let's interpret what we're talking about here. Okay, what does it mean let's talk about some real life examples that we might use composite functions and what it means. So let's think about this example 3. The function c of s gives us the number of calories burned completing s sit-ups. So maybe if you did 50 sit-ups, you'd burn some number of calories. Okay, and S of t gives the number of sit-ups a person can complete in t minutes. So if you said 5, this would give you 5 minutes. How many sit-ups can you do in 5 minutes? The output of this function would be the answer. So they want us to interpret C composed with S at 3, or C of S at 3. Okay? So let's think about the internal function first. What is this? S of 3 is the number of sit-ups a person can complete in 3 minutes. Right? That's what S of 3 means. Okay, well, that's the number of sit-ups a person can complete in 3 minutes. This bigger function, C of S of 3, that's going to tell us, so this is the number of sit-ups a person can do in 3 minutes. This is the output of this is going to be the calories burned by doing that number of sit-ups, right? So altogether, the meaning of this function, of this composition of functions, is the number of calories that a person can burn in 3 minutes by doing sit-ups. Okay, so we've combined those two functions into one function where you say, you give me the number of minutes, I'll tell you the number of calories you're going to burn by doing sit-ups. Okay. All right, let's think about this one, investigating the order of function composition. Okay, so f of x gives miles that can be driven in x hours. Okay, so you tell me the number of hours, I'll tell you how many miles you can drive. All right, here we have g of y. This gives us the gallons of gas used in driving that many miles. So you tell me a number of miles, and I'll tell you how much gas you'll use. So which of these expressions is meaningful? F of g of y or g of f of x? So maybe pause for a minute and think, which of those is meaningful? Okay, you're back. So let's think about this. In this case, our input would be the number of miles, and our output is the gallons of gas. Now, for f of x, our input is supposed to be a number of hours, right? We're looking for this. So this tells, if we put input to f a number of hours, that tells us how many miles we can drive. But the output of g of y is the gallons of gas, right? So this input and output don't really match for this ordering. So let's think about this. If you told me the number of hours, I'd tell you the number of miles we drive in the internal function. And then for g of y, if you know the number of miles, you can tell me the number of gallons of gas. Okay, this is making sense, and the inputs and outputs match, right? So if you tell me the number of hours, then we'll know how many miles, and we'll use that to know the number of the gallons of gas. So combined, you tell me the number of hours you're going to be driving, and I'll tell you the output of this whole thing will be the number of gallons of gas that you'll need, or that you'll use. Okay, so this second expression is the meaningful one. This one doesn't really make any sense. Okay. All right, so now let's practice actually evaluating these, and let's use a table to do that. So let's look at example 5. Here we go. Okay, so let's evaluate a composite function using this table. Using table 1, evaluate f of g of 3 and g of f of 3. Okay, so we already know these could be different. I mean, there could be a coincidence that they come out with the same answer, but in general, the order matters, and these are going to give us different answers. Why don't you just see if you can do this? Pause this and see what you get, and then come back and we'll do it together. All right, so let's find f of g of 3. Okay, so first let's evaluate with the internal function here, g of 3. Well, here's our input, x is 3. Our input, g of 3, is going to be, our output here is 2. Right, g of 3 is 2. So this is going to be f of 2. Okay, and now we evaluate that. We find our input's 2, our output is 8. How about g of f of 3? Okay, well, let's first evaluate f of 3, the internal function. Well, f of 3 is 3. So that's going to be equal to g of 3. And then we evaluate g at 3. So the input is 3, the output is 2. So as we expected, these values don't match, right? The important thing to remember is we evaluate the internal function first and get the output, and then we evaluate the outside function at that value. Okay. All right, let's do the same thing using graphs. Let's use a graph to evaluate a composite function. Okay, so using these figures, evaluate f of g of 1. Okay, well, here's our graph of g of x, and here's our graph of f of x. We want to evaluate the internal function, g at 1. We do that first. Okay, so we'll look at this graph here, because this is g of x. G of 1, so our input is 1, so we go along the x-axis to that value, 1. And our output is 3, right? The y value, when x is 1, g of x is 3. Okay, so 3 is the value of this internal function. So now we want to evaluate f of 3. Okay, well, we've got to hop over to this other graph because now we're finding f of 3. So our input is 3 and our output is 6, right? Our input is 3, our output is 6. So the answer to the whole question, f of g of 1, is 6. Okay, and now let's do one last. Now, so we've evaluated composite functions with tables. We've evaluated them with graphs. Now let's do it with an equation. So let's look at example 7. If I can. Let's see. I'll pull this down. Let's look at this. Given two functions, f of t is t squared minus t, and h of x is 3x minus 2. Evaluate f of h of 1. Okay, so just like we did with tables and just like we did with graphs, we're going to evaluate the internal function first, right? So first we want to find h of 1. All right, so just like normal, we go to this, we'll see what the equation is for h of x. Everywhere there's an x, we're going to put a 1, so we'll have 3 times 1 plus 2. So we get 3 plus 2 is 5. Okay, so we've evaluated the internal function here, and now we're going to evaluate the external function. F of 5 is, let's see, here's the function. It's going to be 5 squared minus 5. So 25 minus 5, which is 20. Okay, so the answer to the whole thing is 20. We can write f of h of 1 is 20. Okay, so there we go. We've practiced evaluating functions using tables, graphs, and equations.